So, am I audible?
Yes, sir.
Yes, sir.
Okay. So, so in the last class, we have discussed about the voltage regulation. So, what is voltage regulation? That is change in voltage from no load condition to the load condition expressed in the terms of no load voltage. Okay. We call it as a regulations. There are two types, regulation up and regulation down. Okay. So when you express in the terms of no load voltage, it is a regulation down. And when you express the change in voltage in the terms of load voltage, then it becomes up regulation. And unless specified, all regulations are assumed to be down regulation. Clear? Okay, the regulation can be positive, it can be negative, it can be zero. So positive under lagging PF, maybe negative, not always, maybe negative under capacitive or leading power factor, and for zero regulation, that is there is no change from no load to full load condition, that you call as a zero regulation condition. Under specific condition it occurs. Okay, power factor and the parameter of the machine transformer that decides the condition for zero regulation. Okay, so now I'll be sharing it the screen. Okay, so we have already studied regulation. As you know, your load regulation is dependent on two conditions. That is load condition, half load, full load, and also on the power factor of the load. So these are some factors which we have studied in the last class. Today we will see about the phasor diagram. Phasor diagram on a load and on no load. No load already we studied. Now we will be studying phasor diagram on various load condition. Now let us say we start with inductive load, inductive or lagging PF load. Clear? Lagging PF load. Now I start. As I told you, drawing is not little bit, it is not so good. So we start with this. This is my phi. And as you know, this will be my E2. It is in E1. So E1 and E2 are in phase. Okay, induced voltage are in phase. Clear? This is there. So this is minus E1. Minus, it is reverse vector, so it is minus E1. Clear? Now when the machine is there, it will draw no load current, which will be having large phase angle under no load. That is, power factor is very low. So, and that will draw a small current called as no load current, that is I0. Clear? And this angle we call as a no load phase angle phi 0. Clear? Phi 0. Now E2 and V2. Actually, under no load condition, E2 and V2 will be in phase equal, but practically it happens that there is a small dip angle V between this E2 and V2. Okay, V2. This is V2. And we are talking about a lagging power factor. What it is, a lagging or inductive load. So the current will be lagging. The current will be lagging by some angle, and say that load current is I2 and the load power factor is 5. Load power factor is 5. Okay. Now actually this angle I0 and V1, that is supply, that is the phi0 angle, but some okay, that angle between I0 and V1 is a phi0, but we are showing it as a E1 because that phasor difference is very small and we can take it as a phi0. Okay, between E1 and I0. Okay, now as you know, I will draw here, your primary will have, here you have no load branch, clear, and this is R1 X1, small x1s, and ideal machine, you have secondary R2 X2 and the load, or you can put it as a V2. This is as a V2, this is as a E2, this is as a E1, and here the voltage is V1. Voltage is V1. Clear? So now we will start our working. Now this is my R1, resistance of the primary winding. We have taken consideration of I0 is flowing through this, and I1, actually I2 dash, not 1, I2 dash, and I1 will be flowing through this. Through this it is I2. Clear? Now I'm saying over here. So when I2 is flowing through this, there is a voltage drop I2 R2 across this and I2 H2 across these parameters. Okay, so we have to consider a voltage drop across these R2 and X2. So it will be I2 R2, and as you know, we'll be adding these drops to this voltage V2, and then I'll get the E2. Okay. So when I add V2, this drop across X2 and drop across R2, I get E2. So actually we started with E2 because it is 90 degree from the flux position that is there. This is 90 degree. Okay. Now the drop in the resistance will be in phase with the current flow. So parallel to this current phasor, I will draw, I'll just add these drops. I will change the colors. So this is my I2 R2 drop. Okay. And 90 degree to that, this is 90 degree. My drawing is not good. You can do. So 90 degree to that, this will be I2 X2, and this is my I2 Z2. You can put it I2 Z2. So secondary side we have completed. This is the phasor diagram. This is the V2 voltage. To that we are adding this drop I2R2 and I2X2 and I get E2. Clear? Now we'll move to the primary side. Okay? Here you can also show I mu, and this will be my I W component of I 0. Okay, so this is my I mu, IW. We will not consider so minute details. So this is I mu, this is IW, which are the component of I0. I0 cos phi 0 is IW, I0 sin phi 0 is I mu, which is responsible for flux. This is for loss. Okay, W is for loss. Now we have to find I2 dash. I2 dash is KI2, that is equivalent on primary side. It's equivalent of secondary current, equivalent I2 on primary side. Clear? That is denoted by the I2 dash. And how do you get? It is by KI2. So I will be transferring this current to the secondary side. It will be in opposite direction. So this is my I2 dash, which is in exact phase opposition to the I2, 180 degree shifted. I2 dash, which is calculated using this formula KI2, you know what is K? It is voltage transformation ratio, which is V2 by V1 or N2 by N1. Now I2 dash and I0 will give me I1. So I'll be adding this I0 like this. This is addition, and I get this current, which is I1. The red one is I1. It is the sum of I2 dash, vector sum I0. Clear? I2 dash plus I0 is I1. Got it? Okay, using this parallelogram, you have to complete and get it done. So I2 dash, I0 is I1. Now I1 is the current on primary side, this. Okay. Now that basically I1 is the actually I didn't, it should be here. This branch should be here. Clear? This branch should be here and R1 X1 should be going. When you draw the approximate circuit, you can neglect this. Just so now can you do it on primary side? Similar method as we did for secondary side. Can you do? I hope you can. Yeah. Please try for this. Okay? Try. Same way. You have to add drop in I1 R1 and I1 X1 to the E1 to get V1. So, see, if you want exact circuit, then this will be here. For approximate, you can put it here. Doesn't matter. But we will now try with the exact circuits. So this branch will be shifted here. Okay. Now you got KI2 equal to I2 dash, and when you add I2 dash to the I0, we get I1 on the primary side. So the I1 will be flowing through this R1 and X1. So drop across this. When you add to the E1, we get V1. So now it will be in the drop across the R1 will be in phase with the I1 resistance. In resistance, current flowing through it and voltage drop across it will be in phase. So that's why parallel to this I1, I will draw a phasor which is equivalent to I1 R1. So this is E1, this is I1 R1, and 90 degree to that, this will be my I1 X1. And when I add these both the drops together, I get, if I put this as a Z1, it will be this drop. When I put it over here, it will be I1 Z1, I1 Z1. So that is this drop. Okay. And when we add this E1 and Z1 I1 drop, we get V1, which is given by this. So this will be my V1. This will be my V1. Okay. And actually this will be the phase angle I1 and V1. This will be the phase angle on primary and this is the secondary. Okay. So you see there is a difference, but we are neglecting it and assuming that 5P primary side phase angle equal to secondary side phase angle, because we want to simplify the solutions. Otherwise, lot of calculations will get involved. So this is my V1. This is the diagram under lagging PF. Okay, under lagging PF condition, where current I2 load current is lagging behind the voltage. Now we will talk about the leading power factor. And before that, we take unity power factor. Let us say unity power factor. This is at lagging. This is at unity PF condition now. Phasor for resistive load. Resistive or unity power factor condition. Okay. So I'll start again. This is my phi. This is my phi. And as you know, 90 degree to that will be E1 or E2. And this is my V2, very small angle. This angle is very small. Just for understanding, I am making it large. Okay, very small, 1 or 2 degree only. But just to have a good look, I am making it larger. Then, as you know, it is a unity power factor. So my current will be in phase with this. So this is my I2. Because it's a resistive load or unity power, current and voltages in the load will be in phase. Okay. So there is no phase angle between I2 and V2. Now, we take this. This is my minus E1 minus E1. And as you know, the current I0 will be here. And using the same relation, you have to calculate the I2 dash, which will be in exact phase opposition, this I2 dash. So it is 180 degree I2 and I2 dash are 180 degrees. And you know, after adding these two currents, I will be getting I. This is my I1. Okay, I2 dash is KI2. Now we'll come back to this. So we have found the currents now. Now I2 and V2 are in phase. So I will be adding drop to this. This is in phase with that. So this drop is I2 R2. Clear? And 90 degree to that will be my I2 X2. Will be my I2 X2. So this is my E2. Got it? This you can show. This can show it as a I2 Z2. I2 Z2. That if I am considering this as my Z2. If I am considering it as Z. So this secondary side is over now. This secondary side is over. Now we'll reach to the primary side. Here you have to show, I have not shown, but you can show E1 here. E1 here. Okay. Now when I come to this side, I will little reduce it. This is not proportionate. I will just make it little bit smaller so that it doesn't get mixed with the text. So this is my minus E1. To this I will be adding the drop I1 R1. Now it's in phase with this. So parallel to this I will be adding this drop. This is I1 R1 and 90 degree to that is my I1 X1, which is 90 degree to that. And when I add this together, I get I1 Z1 drop. It is this one. Okay. Now when I add this I1 Z1 to E1, reverse the E1, I get E1. I get V1. So this is my V1 and this will be my 5P. This will be my 5P. Clear? So I hope we have understood about the phasor diagram on unity power factor or on resistive load. Okay. Now, I think is it possible? I hope so. You can do it here itself. So now we will be talking about leading PF condition. Lead are capacitive. Leading PF or capacitive load. In practice, 90% of the load will be inductive, lagging PF. Very rarely you will find a leading power factor condition, that is capacitive loads. Okay. So now again I start with this. This is my phi. Okay. And 90 degree to that will be E1, E2 I take down. Anything can be there. E2 can be more than E1 or E1 can be more than E2. It is dependent on the type of a transformer, how you connect the source. Okay. Now what will happen? V2 will be there, very small angle, and your I2 will be leading. So somewhere here there is a I2. Okay, and this is my phi 2. Okay, this is my phi 2. In the unity it is in phase, so no phi. That is 0. बराबर है? Now phi 2 you got this V2 I2. Now again I0 is there. Actually I should have drawn this completely. थोड़ा तिरछा हो गया, doesn't matter. So this is minus E1. Now I0 is there. Clear? I0 is there. Now what will happen? I have to reverse this I2 dash. I am making this. So this is my I2 dash, which is given by AI2. Okay? And now when I add this together, I'll get it somewhere here. My current I1 will be there. So this is my I1. Okay, this is my I1. Now at this I'll be adding I1 R1 parallel to this, and 90 degree to that will be my I1 X1. Okay, and when I add them together, I get I1 Z1, but now I'll be putting it like this. Color. Let us take this. So this is my V1. So this is my V1, and this will be my phase angle phi, phase angle on primary side. Okay, got it. So this is how you can plot. Now here we did it for the primary first, and then now we'll move to the secondary. So again I2. So this will be my I2, I2, and 90 degree to that will be, this is I2 R2, which is parallel to this, at 90 degree to that will be my I2 X2. Okay, now I'll just tell you X2. So this is there, and when I add them this drop to this V2, I'll be getting E2. So actually though I draw E2 here, basically this one, basically this point, because of the dry, now this, okay, so my E2 will be somewhere different position. Okay, so load is this I2 R2, I2 X2, and they, when I add them together, I get E2. So this will be my E2 position, huh? And it will be in phase with this E1. So now what I will just rub out this and make little bit smaller than that. So this is my I2 R2 drop, only this much, and 90 degree to that. 90 degree to that is my I2 X2 drop, and this is going to be my E2. Okay, you can put E1 somewhere here. Okay, this is E2. So this is my E2, and this is my E1. So E2 is smaller than V2, that you will observe. This point is I2. This, so V2, we are adding the drop I2 R2 and 90 degree to that I2 X2, and we are getting E2. So this way it will happen. Clear? Clear? Understood or not? Okay, so this is for capacitive condition. Okay, so this phasor diagram are there, and note down. These are very important, because even if you forget a single quantity, the valuer may not give you a mark, or may give you 0 marks. Or if it's a fully correct, then it is a fully, then only you get the full marks. So be careful. Okay. So on secondary, I can redraw this portion here again in a simple way. Okay. I just, this portion, I can do it. See, this is my V2. Clear? I2 is leading. I2 is leading some current. It's leading. Okay. And to this V2, will be adding I2 R2. And 90 degree to that will be I2 X2 drop. Clear? I2 X2. Clear? Like this. This is I2 R2 drop. This is I2. I'm sorry, I did mistake. So I see mistake hai, you will get 0. So I2 X2. This is there. Okay, this drop. And now I'll be getting, I'll be using another color. So this will be my I2 Z2, and this will be my E1. Sorry, E2. This will be my E2. This will be my E2. Clear? Understood? So E2 may be less than, not all necessarily. E2 may be less than V2. Maybe, not completely. Always, not always. Maybe less than V2. Okay? Because practically, when leading PF is there, normally you will have E2 less than V2. But that depends on the value of your power factor or the phase angle, you can say. So this is about the various phasor diagram. So leading PF. So this portion is drawn here, this portion. Okay? Understood now? This is my V2. I2 is leading. So I will be adding I2 R2 drop to this. Then I2 X2, 90 degree to that. This will be my I2 Z2. And when I add V2 and I2 Z2, I get E1, E2, sorry, E2. Clear? So these phasor diagrams are important for us. So this is all about the transformer. Okay, you have to take numericals from some textbooks. Use any textbooks, huh? And try yourself. Even if you take a solved example, doesn't matter. You have to test yourself. Okay, so take unsolved solved example, try it yourself, without looking into the solution, and check whether you get the correct solution or not. If you are not getting correct solution, where you have gone wrong, that you can immediately make out from the solution available in the book. Clear? So this is about the transformer. So you have to do more numericals. You have to do more numericals from any textbooks or reference book and complete. So transformer is produced. Now we will be starting about the motor. So today just introduction. So DC motor. Okay. So we'll be discussing about the DC motors. Already we have seen the classification. So again, there are self-excited, and separately excited DC motor. Okay. And this self-excited can be further classified as series motor, shunt motor, and compound. And this can be further classified as cumulatively compound or differentially compound. Okay, so a DC motor self-excited, further series, shunt, and compound further this. Okay, this is there. Separately excited is there. So we will just see about the basic construction of a DC motor today. Just construction. So construction of a DC motor. Okay. डीसी मोटर देखी है आप में से किसी ने? हाँ, how many of you have seen the DC motor? हाँ, नहीं, no one
इन
has
टॉयज
seen.
सर,
हाँ, in
देखिए सर,
टॉयज।
toys. Yes, it is old toys. You have that is there. Agreed. Basically, mm, there may be some people from rural areas. So on on the cycle, they used to fit some lights during old days. So that was some kind of a DC generator. Basically, the construction as far as DC motor and generator are concerned, it is same. As far as construction is concerned, construction of DC motor and DC generator is same. In fact, at least theoretically, no, though not practically, generator can be used as a motor or motor can be used as a generator, but it is a theoretical. Okay, practically it is not good to use like this. Okay, so the basic construction of the DC machine, rather, instead of calling it as a construction of a motor, you can call it as a machine because both generator and motor will have the same. So something like this is there. I will try to be good in drawing. Okay. So the So now we will discuss about the winding, the construction. So this is my north, and say this is my south pole. Okay, so basically construction will consist of three main parts. Okay, magnetic field system or a field system. Field system. Okay, second one is armature. And third major part is commutator. Plus brushes you can add. Okay. So these are the major parts. Okay. Now we see each part. In the field system, you have, it cannot be shown here in complete way. So just we will discuss about the field system first. So this is outer covering, or we call it as a yoke. Okay. So it's just a cover, protective cover. It has many other purpose also. So here to the yoke you will be connecting or bolting. You will bolt these poles. Electromagnetic poles are there, so you will be connecting these poles. It is poles. When just showing one pole, you can do it on the same thing on the another side. On this pole, actually you have core and shoe, two different parts. So this portion we call it as a shoe, pole shoe, and this is my pole core, and the whole system is a, oh, so the shoe must be laminated. This is always laminated, huh? Means you know the laminations made up of thin sheets, so it is always laminated. Okay. Yeah. And on this we will be putting winding. Okay, so field system consists of pole core, pole shoe, and the field winding. So this is my winding. So we will have field system. We will have even number of poles. Okay, even number, north pole and south pole. So on each pole, this structure will be there. It will, the pole is bolted to this yoke. It may be welded also, it may be riveted also, it may be screwed also. You have to hold it in this. So this is my yoke. To that you will be connecting this pole core, which is again an electromagnet, because my permanent magnet has a very weak capacity, very low flux. So practically for a big machine we will have an electromagnet. So electrical winding will be there, and it will be connected to some DC supply, and you get the creation of a flux. So this is there. So this is the field system. Okay. And normally copper winding will be used. Clear? Understood? Like this. So on this core, copper winding will be put. This is a part of the shoe. This portion. This is always laminated. So this portion is a shoe. Okay. This portion is a core, and on that you will be putting winding. Okay. So this field system will consist of this. No. Okay. The yoke normally will be made up of cast iron or maybe a steel, cast steel. Okay, and the purpose of yoke to protect the overall machine. Okay. Okay. overall machine. It is a protective cover. Protective cover. Okay, that is one thing. And it also, this is the one function. Second function is it flux path is there. So what actually happens when flux is generated in the poles? Okay, that flux will be following this row reluctant paths and it will come to this and it will move like this. So this is my flux. Same thing will be on this side also. Huh? So it also provides flux path, low reluctance flux path. So this is there. So this is my flux field. Field winding will produce a flux and will flow through this path. Okay. So and as I told you, shoe is there. Actually, it supports winding. Okay, this winding is support. That is the function. Supports winding. Supports winding. And it increases the cross-sectional area, thereby reducing the reluctance. Reducing the reluctance. So that is the purpose of this. Okay, then. Hello? Please repeat.
Increases, sir.
Huh? It reduces reluctance. It reduces. Put it in a chart. I will read the chart. Not able to. Huh? Put your query in a chart. I am not able to. Huh? Put your query in a chart. I am not able to understand. Not able to hear properly. It increases cross-sectional area. This cross-sectional area, because of this is a core, so cross-sectional area of this and the shoe. So shoe increases cross-sectional area. And as you know, therefore it reduces the reluctance, which is good for the machine. Okay. So you need even number of poles. Even poles are needed. Now we talk about the armature. Armature is having core. I'm showing you the separate parts. So this is my armature. Okay. So armature has a core and these teeth are there all over the periphery. I have not drawn it. Like this. Okay. Like this. I'll just make it little bit good to appear. So here you have this structure. Okay. We call this portion as a teeth and this deep portion we call it as a slot. Okay, we call it as a slot. So the core has central hole is there. Okay, and this is on the periphery of the laminations. This is always laminated. Huh? So here you will be putting in the slot, coil or a conductor will be put. Okay, coil or conductor will be put. So I'll be putting these conductors in each slot like this, like this, like this. Okay. So these are my conductors which are put. So this is my conductor. Clear? So in the slot, conductor is put, and actually, technically speaking, conductor, turns, coil side, these are different things. But for us, it is one and the same thing at first year level. Clear? We cannot study all things in detail. So conductor, turns, or a coils, it is one and the same thing for us. So these are there. And they are connected in a particular fashion, and we make it as a armature winding. Okay, armature winding. So the conductor are nothing but a armature winding or armature coil. And basically, how you connect it. Okay, so based on the different connections, we have a different types of armature winding. One is lap winding, another is wave winding. Okay, so that is dependent on how you have connected these conductors. So don't worry what is about how wave is done and how lap is done. That is for the electrical student. In second year machines, they will learn how they are connected. Clear? And this is a okay. So now I'll just draw one or two this. So this is my armature. Here are the subconductors. Okay. Now the ends of these conductors, here this is the place for a shaft. Shaft will pass through this hole. Clear? Now on the same shaft, the armature is there, and this armature coil or armature winding is connected to a copper segment. So these are the copper segments or copper bar, you can say, big bars. So after doing connections, the armature coil, each coil will be connected to this bar, and we call them as a commutator bars. Okay, so this thick bar will be called as commutator segments or a bar. Clear? So this armature conductors are connected to the thick copper bars, and again this will be there. Okay, and each bar is insulated. In between these two, they are separated by a sheet. Okay, they are separated by a sheet, and normally it's a mica sheet. So these commutator segments, they are separated by this mica sheet. Okay, so these are the commutator segments. Clear? So armature, you have a core having slot and teeth structure on the periphery. In the slot, conductors or coil will be placed, and they will be connected in a particular fashion, and based on that it may be either lap winding or wave winding, and each end of the coil is connected to the thick bar, which we call as a commutator segment. So basically the appearance will be something like this. This is my armature. I'm drawing now a very simple diagram. This is my shaft. Okay, shaft, which is passing through this core. And this is my armature. I'll just make it different. So this is my armature. Okay, armature. This is my armature. And each segment of the armature, you will have slant type structure. So I can just take this color, and here there is a different color. So this way. So this is armature, and these copper bars, we call it as a commutator segment. So like this, it will be appearing like this. This is having a larger diameter, and there is a slant structure on this. Okay, so this is forming my commutator. Okay, commutator is connected. Each coil is connected to the separate commutator segment. So like this is my commutator. Okay, and you need a brush. So brush will rest on this. Here there is a brush. These are the brushes. Okay, positive brush or negative brush. So on this side also there will be one brush. So this is my brush. Here, this is a brush like this. So this is a brush. This is also a brush. Normally carbon brush will be used. There is a reason for that, but we will not enter into those details. So carbon brushes are used, and these carbon brushes, it is not just brush, it is a complete assembly. You have to keep continuous contact of a brush and commutator segment. So it is put under pressure. So you get some brush assembly ladder, where you have a spring pressure carbon brush under pressure. It is kept by the spring in the built in that assembly of a brush, so that because you want a continuous and perfect contact of the brush and the commutator segment, otherwise there will be a sparking. And these brushes are used there for collecting current or sending current. Collect or sending. If it's a motor, we will be sending current. If it's a generator, we will be collecting current from the brushes. Clear? So this is there. Okay. I hope you understood about the structure of the motor now. So in the construction, this is there. So it's armature, and this is my commutator, and this is the shop position. Clear? So I hope you understood about the construction of a DC motor. Okay? And you see, you have to use good material for the core so that the losses will be minimum. And sometimes if it's a big machine, there you will find holes here on the core. Okay, armature core. And this is there to send cooling media, because there will be a losses in the core and it will raise the temperature, and that you have to bring it down to maintain the temperature of the machine within certain level. So cooling media will be sent like water, or it may be hydrogen, or it may be forced air itself. Okay, so cooling media will be passed through these holes which is there in the core of a armature or armature cores. Clear? So armature core will be consisting of various lamination. Normally cylindrical laminations will be there. Okay, so it will be cylindrical in shape. Same method, one lamination put over another lamination and pressed under the hydraulic press, so that you get a solid structure and appears like this as a solid structure. Clear? So this is armature, and this is commutator, this is brushes, and this is a shop. Here you can put some kind of a pulley to take output, mechanical output. Input is electrical. So what is motor? Motor basically converts electrical input to the mechanical, and then it becomes a motor. Okay, and if you are giving mechanical input and converting into electrical, then it becomes a generator. As far as DC is concerned, DC machine is concerned. Okay, so this is about the construction of a DC motor. Clear? Now, normally, just 1 minute, you can have more than one winding on the same pole core. Okay, so the winding may be multiple, more than one. It may have 1+1 winding on the same core. Okay, more than one winding may be there. on the same pole. I have shown just one, but you may have more than one winding, copper windings, maybe more than one. So this point you note down, and here we stop now.